Hello everyone. So today we are finding the absolute maximum and minimum of a function f of x, y, z, which is equal to x, y, z to the 1/2, subject to x plus y plus z equals 1. So you have a function and it's subject to a constraint, and here x, y, and z are all greater than or equal to 0 as well. Now, typically you would use Lagrange multipliers to find both the absolute maximum and minimum. But the purpose of today's video here is that sometimes this method, Lagrange multipliers, doesn't help with finding one or the other of the values of the maximum or the minimum, the location. Now, why is that in this case? Well, let's start by looking at the partial derivatives of f. So fx, fy, and fz, and if you look at them, all of them do not exist anywhere where x, y, or z equals 0, okay? And x equals 0, y equals 0, and z equals 0 are places that are included here in your constraint, okay? So again, the constraint is x plus y plus z equal to 1, where x, y, and z are all greater than or equal to 0. So these are all part of that constraint. And the issue with that is if you look at Lagrange multipliers, this is one of those cases where you look at the theory to see why something doesn't work out here for you. Lagrange multipliers in particular says that if f of x has continuous partial derivatives, as well as g of x, y, z, and that's your constraint, then you're going to find your extrema by applying, Lagrange multipliers. When I mean apply, quote unquote, is when we do the whole lambda, the gradient of f equal to lambda times the gradient of g, okay, what I have boxed in. However, in this case, this will the point anywhere involving 0, if I have a constraint anywhere where x, y, and z are equal to 0, Lagrange multipliers won't find that, okay? So Lagrange multipliers can find any other point that where the partials do exist. And so if we were to start looking at that, first of all, fx, fy, and fz are already given above. And g of x, y, z is basically x plus y plus z. It's like the constraint equation. And if you take lambda of g, you get 1, 1, 1. And if you compute with what Lagrange multipliers tells us to work with, you would get what you see right here, okay? And amplifying that over here, you get such. And we start solving these equations, and one thing you could start by doing here is that if you take equations 1 and 2 and you set them equal to each other because they both equal lambda, I won't do the work, but it would give you this result right here where yz equals xz, which would imply that y equals x or z equals 0. So I'd suggest you stop that, maybe stop the video for a second and take a look at that. And z equals 0 is not possible because of what we just spoke of, the partial derivatives doesn't exist at 0. And likewise, if you took equations 2 and 3 and you set them equal to each other, you would get z equals y and x equals 0. Again, x equals 0 is not possible. And the next step with Lagrange multipliers is once you find some relationship between the variables here, you use that relationship and usually replace variables in the constraint equation. So yeah, if you took y equals x and z equals y, or x equals y and y equals, as I have it written, and you replace those variables, you get y plus y plus y equals 1. So y equals a third, z equals a third, and x equals a third. So that point right there can give us a possible maximum minimum. Okay, we'll take a look at that for a second. How about though, let me go back to looking at what can happen when x equals 0, y equals 0, or z equals 0, okay? Finding for extrema. So here, again, Lagrange multipliers does not apply. And when you have a case like this, you kind of have to look at this, kind of think about it for a second here. And if you think about the points that are restricting you, x equals 0, y equals 0, z equals 0, first of all, there's an infinite number of points for which fall in the constraint, meaning that x plus y plus z equal 1, but for which those points would give you 0, and for any one of these points, x, y, or z equaling to 0 would work. So for example, if you take the point 1/2, 1/2, 0, that is on the constraint, because if you take 1/2 and 1/2 and 0 and add them together, that equals 1. and z would equal 0. You plug that into your function, you get 0. F of like another point would be 0, 0, 1. That gives you 0. And if you plug 1, 0, 0, and that gives you 0. Yeah, there's an infinite number of points where what I'm saying here is that either x, y, or z are equal to 0, but fit into the constraint, okay? And what I'm trying to get at is that every one of those points where either x, y, or z equals 0, when you plug them into your function, give you 0. And I would say 0 would be your absolute minimum, because the square root function itself is always greater than or equal to 0. So 0 would have to be the minimum value, and you do achieve that when either x, y, or z equal to 0, okay? So that's how you would look at basically those exceptions to Lagrange multipliers. Again, the exception being when x, y, or z equal to 0. Kind of go back and see what would happen under those cases to the function. And the absolute maximum would actually occur at 1/3, 1/3, 1/3. If you plug that into your function, you would get square root of 1 over 27, or 1 over 3 root 3. And you know this is a maximum because if you test one, it satisfies the Lagrange multipliers, but the other thing is to make sure you pick some points that are in the constraint and put them back into your function. So let's say 1/2, 1/3, 1/6. So 1/2, 1/3, and 1/6 adds up to 1. But when you take the square root of this number, you get 1 over 36, which is 1/6. 1/6 is smaller than 1 over 3 root 3. My point being is like, yeah, any point that you pick will be smaller than that. So then 1 over 3 root 3. So this would be your absolute maximum, okay, from Lagrange multipliers. So again, this video was about working with a point for which Lagrange multipliers doesn't apply on a constrained extrema because of differentiability not working out. All right, I hope this helps. Thank you for your time.